Good day to everyone. Myself, A.S. Syed Shaul. I'm currently pursuing my PhD in Computer Science at the National Institute of Technology, Puducherry. My research interest lies upon application of reinforcement learning to function optimization, essentially a congruence of RL and optimization. In this short video, I'll be explaining what is function optimization in a hopefully relatable and understandable manner. Let's start. Problems are of many kinds, but in general, given a problem, we expect it to have a solution, typically a unique solution. Most of the problem we come across in our academics and exams are of such kind. Given a problem, we expect it to have a unique solution and we try to get the solution by solving the problem. This is the normal case. But this is not the only type of problem that exists. There are different kinds of problems, or to be specific, different classes of problems out there. Optimization is one such interesting class of problems where, given a question, you have multiple solutions, and interestingly, all of these solutions are correct. What is interesting is if you have a problem that has infinitely many correct answers to it, what is there to solve for? Here comes the twist. We are not interested in the correctness of the answer, rather, we are interested in the quality of the answer. Out of all possible solutions, how good is a particular answer or a solution? That is where our interest lies upon. A problem may have many solutions that satisfy the constraints of the question, but we are interested in the best or the most qualified answers. So, to summarize, an optimization problem has a specific problem structure to it. Given an optimization problem, you would have infinitely many solutions to it, and the goal is to find among the all available solutions the particular solution which gives me the maximum benefit. Simply put, return me the best solution of all the available solutions. I hope you can intuitively connect to this. During our day-to-day life, if we come across the term optimize the situation, typically this will involve multiple options available to you where you may try to choose one over the other. The options themselves may not be necessarily right or wrong, but you are interested in the best out of all the available options. That is why people often combine the term optimal with things like diet, workout, nutrition, etc. You may have many different diet or workout plans, but of all the available plans, which particular one will give me the maximum benefit? That is the question of optimization. So this is a problem structure optimization problems have in general. So this is the official definition of optimization given by Wikipedia. Take time to read through this. Okay, now let us see an example to further understand the problem structure of optimization problems. This graph corresponds to SVM in machine learning. SVM stands for Support Vector Machine, which is a ML model used to classify data points. In this particular example, the goal is to classify the blue circles and the red boxes. The idea is to come up with a line, or to be specific, with a hyperplane that best separates the data points. One can immediately see that there can be infinitely many lines or many hyperplanes that can correctly separate the blue circles and the red boxes, as shown in the left graphs. Here, correctness refers to the fact that the line successfully separates the data points. But visually, it is easier to understand that though all these lines are correct per se, they are not optimal, or simply put, it doesn't seem to be good enough. Some lines are quite closer to the data points, some of them are in weird slanted angles, so and so. So the SVM model is designed in such a way that it always tries to choose the best or the optimal line of all possible lines. The right graph shows the best line or the hyperplane that SVM will choose. Here, the task of separating the data points is the question. The multiple lines or the multiple hyperplanes shown in the left graphs are the many available correct solutions. And the right graph shows the one particular solution which is the best solution or the optimal solution out of all available options. I hope this example made you understand the structure of optimization problems in a relatable manner. It is important to understand that in an optimization problem, given a solution, there should be a metric or a criterion that can numerically quantify how good that particular solution is. Let me repeat, a metric or a criterion that can numerically quantify how good that particular solution is. For example, in the SVM graph shown in the previous slide, the cost function of the SVM algorithm says how good a line is in comparison to the other. Without this cost function, the SVM algorithm simply has no means to judge how good a line is in separating or classifying the data points. Technically, the cost function, or to be more specific, the objective function, is the metric or the criterion which quantifies how good a solution is. The input to this objective function, that is, the input is nothing but the solution, comprises of different subcomponents. And these subcomponents are called as decision variables. The solution or the input typically comprises of different subcomponents, and these components are called as decision variables. The number of decision variables is dependent on the problem. Each of the decision variables may take different values and in turn give rise to different input combinations to the objective functions. And for every different input, the objective functions gives out a different value. The idea is to find the right combinations of the decision variables that either maximize or minimizes the objective function. For any real-world problem to be optimized, the first step is to come up with an objective function with proper constraints. This is typically known as modeling the problem. This slide gives definitions of some basic terms. Before proceeding further, it is important to note that the optimization can be either maximization or minimization. That is, out of all possible solutions, you are interested either in the solutions with the maximum reward or the solution with the least cost. If your problem statement demands a solution with the maximum quality, then you have a maximization problem. Or if your problem demands a solution with the least cost, then you have a minimization problem in hand. Mathematically, there is no much difference between maximization and minimization. So, in this discussion, without loss of generality, we will focus only upon function minimization. That is, give me the optimal solution with the minimal cost. Optimization is essentially searching. By this point, I hope you have got the idea that optimization is fundamentally a search problem. Out of all possible options available to you, you are in search of the one particular option or solution which yields the maximum benefit or the least cost. So this is nothing but a search process. So essentially, optimization is nothing but a search for the right combination of the input that satisfies my objective. Now, let us see the mathematical definition of optimization. Mathematically, optimization is given a real valued function f of x, find me the particular input vector that minimizes this function f of x. On a closer observation, the function can be of d dimensions, which means you have d variables or d options. To be specific, d decision variables. Okay, the vectors LB and UB are the lower bound and the upper bound vectors, which defines the values that each of these d decision variables are allowed to take. The lower bound and the upper bound vectors defines the feasible region within which the search for the optimal solution occurs. So what is happening here is you have a function which takes a vector as an input and the function spits out a value as a response to this vector. If x is the input vector, then f of x is the output thrown at us by the function. The input vector x is free to take any value within the feasible region defined by the lower and the upper bound vector. For example, look at the graph in the screen. The bottom xy plane represents the all possible values that the input vector x can take, and the z-axis represents the function value. For each combination of inputs, there exists a value written by the function in the z-axis. The z-axis can be viewed as a qualitative metric which quantifies how good a particular input combination is. In minimization, this is called as the cost function. The lower the function value, better the solution is. If you look closely in the xy plane, the range is fixed from -2 to 2. This is the lower bound and the upper bound vector. The xy plane at the bottom defines the feasible region for this particular example. Now the question of optimization boils down to the following statement. Of all possible values x1 and x2 can take, we are interested to find that one particular combination of x1 and x2 where the global minimum occurs. That is, give me the vector x which has the least cost. To make things clear, let me give you one last example for a better understanding. Let us see a practical example of optimization. Consider the problem of making concrete. The process of making concrete involves many variables. But for our discussion, let us restrict ourselves to 3 components: cement, gravel, and sand. For each of these components, we have a wide varieties of choices available. I have shown few of them in the slides. There are several types of cements available, different types of sands, and different sizes of the gravels. If you mix any type of these 3 components, you will end up making concrete. But for each combination, the strength of the concrete will differ. So the interesting question to ask here is, of all available options for the cement, sand, and gravel, which particular combination will yield me the maximum strength? If we relate this concrete example with the mathematical definition of optimization we discussed few slides back, then for this particular example, we have 3 variables as the input here. A three variable input indicates that the vector, that is the input vector, has three variables or components. For each of these individual components, we have a specific set of allowed values it can take. The lower and upper bound vector defines this set of allowed values for each of the components. Now, if we consider only the discrete possibilities, then look at the number of possible input combinations we have. It's more than 150 million. Now imagine if real values are allowed. For just three discrete variables, we have 150 million input combinations. So out of this 150 million discrete input combinations, return me the particular combination which will give me the maximum concrete state. This is optimization. In practice, the number of decision variables will be more, and they are often allowed to take real values. It can be of 10 dimension, 50 dimensional, 100 dimension, any number of decision variables are typically allowed. So in reality, the total possible input combination allowed is exponentially large. That is, the feasible region may be exponentially large in most of the cases. It is almost impossible to go to each and every input combinations and find which one is the best out of all of them. So instead of brute forcing the feasible region, the field of optimization algorithms tries to find the best choices for the decision variables in a smart way. Now, if we come back to the graphical example, I believe it will be more relatable. Take a minute to understand the analogy between the concrete example given in the previous slide and this slide. The input vector or the combination is nothing but actually a point in the feasible region as shown in this figure. With this, we come to the end of the presentation. I hope this was something useful to you. These are the three papers I have published on optimization algorithms. The code for all the three optimization algorithms are available on my GitHub repository. I have given the link to the PDFs of this paper in the description. I plan to discuss these algorithms in the YouTube videos in the future. If you have any doubts, suggestions or improvements, kindly comment below. Thank you. Have a good day.